Welcome back to the course on wheeled mobile robot. So last class what we have seen is actually like kinematic control along with simulation. This particular lecture would be focused on the another class called dynamic control of mobile robot. So here what we are trying to do, so we are trying to see how the second order error dynamics can be brought, and we will bring one specific you call control scheme called computed input control, or you can say computed input, which is what you call computed torque or force, that we will bring it. So in the sense we will try to see how that particular control scheme can be brought, and then I will explain how to do simulation by yourself. So in this particular lecture I will not be showing the MATLAB simulation, but I will explain how to do by yourself. So in the sense you will also start learning. So let us move to the slide. So where we would be talking about dynamic control. In specific we will see that what is inverse dynamics, how that is different from the closed loop. Then we will take the simple feedback control based on PD. Then finally we will come back to the what you call computed input control, which is generally in robotics what they call computed torque control. So the computed torque is the odd word for us because we are not computing all the torque, but if I bring the wheel along with motor, then the computed torque would be the proper word. But right now I am generalizing as a computed input control. And the final what I will be showing that how to simulate yourself in, you can say, MATLAB with this particular control scheme. So let us start with the very basic. So what we did in the earlier case, the same way we will see. The motion control will start with a given, which is what you call desired, available, all those things we will see. So we will see like what are the desired here. The desired would be here what you call given desired trajectory, which would be consist of eta desired, eta dot desired, eta double dot desired. So these all would be given to us. So in the sense desired position, desired acceleration would be given. But if it is actually like set point control, but you want to do it in dynamic, then these two would be 0, that you need to note it down. Then what would be available in kinematic control? We have assumed that only positions are available, but now it is a second order system. We assume that both position and as well as velocities are available, in the sense actual positions are available and as well as actual velocities are available. Further we are trying to map between body frame to what you call inertial frame. So then we assume that the Jacobian matrix is clearly known to us. So this matrix is available. Further, if we are doing in a probably model based control, we already see what is model based and motion based. If it is actually like model based, then the model also available, in the sense you would be knowing the inertia matrix accurately and as well as other effects also accurately. So these all actually like available. So then what would be the objective or to find? So we are trying to find out what would be tau. So that is what you call control input. So this control input you want to find with the objective of what you call, so t tends to infinity, so my error tends to 0, right. So this is what we have done for what you call kinematic control, but right now it is actually like dynamic control. So your velocity error also supposed to be 0. So this is what your objective. In order to fulfill this, we will actually like take it that as objective, okay. So now what we can actually like see that the asymptotically stable is what we wanted. So this is what we are looking at. So in this case sometime we may use this. Why? We may actually like try to write this tau eta straight away, and then we will apply this J transpose of tau, you can say eta as tau. In that sense we will do everything in one, you can say, coordinate, and then we will bring it to the body as it is. So this is also like can be done. So in that sense what finally we are trying to see, so these errors supposed to be 0. So this is what we are interested in dynamic motion control. So now if you want to do this, what one particular aspect, so we are looking at this. So this second order error dynamics, what you call, so this if I actually like make it as 0, so this is the second order error dynamics. If I achieve this, I am already done the required task. So for that what I required that the mathematical model is accurately known to us and all the initial conditions are same as you call the desired initial condition. Then what we can do the inverse dynamics, right. So that is what initially we start attempt. In fact, in one of the dynamic simulation, you can say lecture, I was showing that how this inverse dynamics can be incorporated. So this is what you call inverse dynamics, but the inverse dynamics would be applicable where the mathematical model is accurately known and then the desired and actual initial conditions are same. Further, you call this eta desired dot and eta desired are non-zero, then only this would be workable, right. So, now we will actually like see how that can be incorporated. This is what I was saying. So, now you can actually like bring this eta desired dot in terms of what you know, okay. So, that you can actually like bring it and then you can see. So, these are the what you call desired, you call trajectory information, right. So, that you can incorporate and do it this. Once you know this and then you can do it. So, in the sense this also you need to write. So, these are actually like available to us and then you are actually like using it. So, these all actually like what you have seen as a inverse dynamics as a open loop, which we simply call for feed forward control, but feed forward control won't work for all the cases. So, this condition is not all the time true. So, then what we are actually like interested, we are actually like interested to see what is the feedback control. So, one of the easiest option, so already in the kinematic or you can say the introduction lecture itself I told. So, the first choice of control in robotics is PD control. Why? The open loop control or open loop system is actually like unstable, but if you incorporate PD control, the closed loop control is straightforward as a stable system. So, in that sense the first choice of control is PD. So, that is what we are trying to see. In that sense what we are seeing that the position errors and its time derivatives are available to us. So, if these are available, what I can write? So, Kd into eta tilde dot plus Kp into eta tilde I can assume as my tau and then I can, you can say incorporate. This will work, but only thing this would be actually like based on the choice of Kd and Kp. So, in the sense the Kd, Kp you have to tune. So, most of the cases this tuning is as the bigger issue. So, that is why we are moving the other control, okay. So, how that is actually like coming, this is what the control aspect. So, this is the proportional control and this is the derivative control and we are actually like assuming that this is not velocity error. We are taking time derivative of position error we have incorporated. So, in that sense what we have to see, so how this Kp and Kd can be chosen. So, since the D is actually like one matrix, so you can actually like take Kp and Kd in such a way that these are actually like somewhat related with one simple parameter called K. This Kp I am taking as K squared and Kd I am taking as 2K. So, then this will give a simplest model what you call critically damped system, but you have to be very clear that these are matrices. So, then what you supposed to know, so this Kp matrix supposed to be positive definite and as well as for simplicity we wanted actually like symmetric matrix also. In the sense Kp transpose equal to Kp and this is positive. The similar sense you can actually like take it this also, okay. The Kd matrix also like supposed to be positive and as well as symmetric matrix. So, even most of the cases what we usually take a diagonal matrix which is very simple. So, diagonal matrix with all positive constant that will also work. So, now we will actually like move forward. So, what it says, it is purely feedback control, but this performance is purely depend on this choice of Kp and Kd. But this is not the, you can say, right perspective, because if you look at the PD control performance, this would be having a, you call steady state error. So, this steady state error would be execute. Sometime actually like it would be having what you call a overshoot, in the sense it would be a underdamped performance. So, these are actually like supposed to be avoided, and as well as we will try to make it the complete error dynamics as a second order error dynamics. In this case the error dynamics is not that way. You see this is what, so you have equation. So, this is what you are actually like substituting as this, right. So, this equation is not giving any, you call guarantee that the eta tilde tends to 0 when t tends to infinity. So, this is not guaranteed, right. So, if this is not guaranteed, then what is the point in using this PD control? That is what the whole idea, that is why we are bringing the new control called computed torque control in general. Here I am putting computed input control. What that means? So, I am assuming that the both position error and its time derivative, or sometime here we are going to call velocity error, are available. Further, what I am saying that the mathematical model is accurately known. What that means? The D matrix and n vector is accurately known to us. So, if this is known, so what we are actually like rewriting this. So, this is what our interest. I am assuming that this is k1 eta tilde dot and k2 eta tilde as this. So, now I am rewriting this. So, what this I can write as, so the error of, you can say, the position, acceleration, and you call the velocity. So, I can rewrite this. So, I am keeping this as it is. So, I am just putting a bracket just for your understanding. This is also like eta desired dot minus eta dot. This is eta desired minus eta, but I am not doing it. Why I am actually like rewriting this way? You can look at it this. What is this? This I can rewrite in the other form. So, what is this? This I can write in the form of what you call D matrix. So, for that what we know, the eta dot I can write as j of, you can just I into z eta. So, from there what I can do? So, I can do it this. Right. So, I can do it. So, but what I know, this is actually like having a control input. So, that is what I am trying to do. You can see, so this is what I know. Okay. So, here what I am trying to do, I am trying to do this equation. So, for that what we are trying to bring, so probably I will actually like recall that itself. So, this particular slide itself, and then I will actually like incorporate one. Okay. So, what we are actually like interested this, right. So, I will rewrite that whatever I have written. So, further what we know, so this we know, further we know like j of psi eta is eta dot. Okay. So, then I differentiate this. So, I will get j psi eta dot plus j dot of psi eta, right. So, these are available. I am trying to recall this. So, what I did? So, I did, so this. So, I am just rewriting this as it is. So, then what I can resubstitute this as this form. So, I will rewrite that. Okay. So, this is actually like replacing this plus k1 eta tilde dot plus k2 eta tilde equal to 0. So, here what you can actually like again know from this equation I rewrite that. So, I am writing that. So, this equation I rewrite the eta dot, sorry, zeta dot I can write as tau minus n of zeta, this whole multiply with, you can say, D inverse. So, this equation is available to us. So, I am resubstituting that. So, in the sense, so what that is D inverse into tau minus n of zeta, right. So, this is the first equation. The remaining I am keeping it as it is. So, what that means? So, I am keeping it as it is. So, I am just putting j dot psi into zeta plus k1. So, now what one can actually like note it down. So, here you can note it down, this is what my control input. I can choose this tau based on rewriting this whole equation. So, what I can rewrite this whole equation, I can keep it thus. So, I can actually like bring that. So, what I can rewrite that equation from this. So, I am actually like rewriting that. So, everything else is the other side. I am keeping it only this term. So, in the sense what I am doing it. So, the D inverse of tau minus n of zeta I am keeping it. So, the remaining all I am actually like bringing it the other side. So, in the sense what you will get. So, this I am actually like multiplying and putting it. So, even I will actually like put this what you call J inverse also. So you can just take it. So this also like exists. So now this is actually like remain as it is, but there is a negative sign. So I assume that this went the other side. The remaining all retain in one another side. So in the sense eta double dot desired minus j dot of psi, then eta, so zeta, then what else? So these all remaining. So k1, so then plus k1 eta tilde dot plus k2 eta tilde. I am actually like again rewriting this. So this whole equation, so I am actually like putting J inverse of psi. So then what remains? So D inverse into tau minus n of zeta, right. So I am again rewriting this, I call this as capital X. So this capital X remain. So now what it remains? So I take it that, so D into this J inverse of psi multiply with capital X. So then this is actually like tau minus n of zeta. So I am writing tau as, so D into J inverse of psi x. So then what you have this. So now this is what you call, you have computed the torque based on what you have your model. So this is actually like your model. These two are come from model and this come from your feedback, where you can see that the aerodynamics become second order aerodynamics become 0, in the sense both are actually like going to be converge. So that is what we are actually like trying to see. So that is what we have substituted here. You can see that I rewrite that in a general form. This is zeta dot and this is actually like your, you can say positional information and velocity information based on error. This is a position error and this is a velocity error, and where there would be two gains. I am assuming that this is a PD control, where this is a proportional and derivative control, and here you can see that this is actually like coming from the desired acceleration, which is nothing but a feed forward. So you have actually like got the feed forward term, and this is actually like you are compensating. So here actually like you call, so in the sense what you call linearizing your model. So this is, so linearization. So this is linearization and this is what you call, you can say scaling. So scaling yourself, okay. So now what it is giving, so you are getting the tau directly. So this is what we call computed torque control in general. Right now we said that Fx, Fy is not torque, right. So you may feel that the tau vector would be consist of the three quantity as Fx, Fy and Mz, where only one is actually like torque. So that is why I modified as computed torque control as computed input control. So now you can see that this is the control activity. So now you can actually like take this forward and you can actually like substitute in the simulation model and then do it. So now I expand this further. So what you get, so you get the overall equation as like this. So this is what your tau equation. You replace what you have done earlier. So what we have done earlier, so tau is actually like you can say gamma into kappa, right. So now you replace that into this and you actually like run the simulation, you will get it. So now this is one stage. The second stage, once you obtain this tau, then you bring it back. This tau you can rewrite as gamma into kappa. So now you wanted to find what is the individual wheel forces. So you would take a gamma inverse into tau. So this you can do it. So this is what you wanted to do it in MATLAB simulation. I expect you will do yourself, because we have done lots of simulations and we have actually like modified everything. So that is what I am expecting you to do it. So this is a combination of what we are doing. So you are taking a feedback and as well as feed forward. So that is why it is called feedback and feed forward combined. So it is actually like computing the input control. Again here the performance is based on the choice of Kp and Kd. Here you can straight away you can take Kp as what I already mentioned, k squared, and Kd as actually like Kd as you can say 2k. You can straight away take, in that sense what it look like, the performance is actually like critically damped. Based on the k value, the rise time would be getting decrease or increase. If you increase the k towards infinity, this rise time would be shorter, in the sense it would become faster. So it may be faster like this, okay. So now you can try to do the simulation yourself and get to understand. So that is what I am actually like asking you to do. We can replace the input vector based on the dynamic control scheme with the existing MATLAB code. I hope you have already the MATLAB code and perform the closed loop simulation. So once you do and comfortable in this KP and KD choice and you have done without any restriction, then you do the further end what that. So you substitute this and see whether your kappa is actually like how much it is coming. So based on that you can actually like choose your control input, or you can say your wheel motor and all you can choose. Your wheel motor is not sufficient, then you can even try to see what you can actually like make the frictional component. Right now you are taking a plastic wheel, you can take the plastic wheel with one rubber strip. So your rubber strip is not sufficient, then you take it a complete rubber strip as a stick. So if that is also not done, then you can actually like make a probably a, you can say knurling on that, in the sense you make a grating. So then you will get a friction more. So that kind of thing you can do it. So that is what I was actually like expecting in this dynamic control. So with that, this dynamic control part is over. So now we will move the next lecture with combination of kinematic and dynamic, that is what we call cascader control. Some people call it as a backstepping. How it is backstepping, that we will see in the next lecture. Until then, see you, bye, take care.